Well, good afternoon, everybody. This is architecture session, and I'm Steve Schrader. I have written most of this presentation, but of course, I didn't do this in a vacuum. I had lots of help from a whole number of people throughout the Mobiveil and other people's experience as well. Let's see, we'll get started here. First, some background on the history of ECC. Originally, ECC blocks were, in disk drive technology anyway, were something that was kind of stuck on. They got tired of doing offsets to read data, that sort of thing, so they got an ECC block in there. And it took up a terribly little amount of space at that time because it was doing 4 bits of correction. Very quick, very easy to do. You assigned one guy to kind of put him in the corner and let him have fun with the ECC block. And of course the disk drive itself was milliseconds of latency, often for average seeks and that sort of thing. So this block was a very small part of the transaction. Then we enter in with flash, and now the ECC block is gone from, it has basically the same performance in terms of throughput, but now it's not correcting 4 bits, it's correcting 60 bits. And instead of getting used every once in a while, it's getting used being pounded by many banks of flash, bringing data through it all the time. And these flash devices, of course, had a lot lower latency themselves. The interesting part here is that, of course, ECC, even though you had multiple devices, you don't have an ECC block per device. So it's kind of forced serialization through this ECC block. One thing nice about these ECC blocks is they were very deterministic. You know, you could run data through them. They came out in specific order at specific time. Of course, you can't talk about anything that has any latency without talking about tail latency. And I'm sure you've heard this a number of times, but it is important for ECC, and especially under certain conditions. So to define tail latency really quick, you have a web server. It launches parallel transactions to a bunch of data servers. They might go to other data servers, but sometimes it's just a lot of SSDs. And if you have one SSD that every once in a while has to have a longer latency, when you combine all of them together, since everything's launched in parallel, the likelihood is that every time you do a transaction get, you're going to get the longest latency. And it's only one of them or 2 of them that are causing this latency, but the whole transaction sees it because they have to have the whole transaction back before they go forward. This implies that the SSD really needs to minimize latencies that are not consistent. It's an important aspect of ECC design. Okay, BCH was interesting, it's quick, it's consistent. You can guarantee that a certain cycle later, after raw data appears, that the corrected output will start flowing. You know, on cycle 27 that bit 5 will come out, whatever. This is, as far as engineering is concerned, this is a dream, right? Because it behaves in a very specific way. You can optimize it. The problem being here for attributes of BCH is the ELP and the chain search modules grow linearly with error correction amount. So as the number of bits to be error corrected grows, those 2 modules grow linearly. And the chain search especially grows more than linearly because it becomes so big that physical size of it alone has requirements of gathering the data so the XOR register, which corrects the data, can function. And of course that's its biggest drawback. But other than that, it has a very consistent performance profile. Now we go into attributes of LDPC. So in LDPC we have raw data come into what's called a log likely ratio buffer. It accumulates the data, it's sent into a correction buffer, and the LDPC core corrects it in place. It has the ability to change a particular bit more than once as its algorithm corrects. And once it gets done, it can send the corrected data out. The actual correction buffer in most of these is in 2 different places, so it can switch. It can go from one to the next without a delay. The LDPC core itself goes through a set of iterations as it does its work. And this iteration, it goes through all the data one time, and that's called one iteration. And once it does that, it can know if it has corrected everything or if it hasn't. If it's done its work, then it sends the data on. The result of LDPC failure to correct is the iterations continue to climb without stopping. You know, our average is about 3.5, but sometimes it can go up to 8, 10, 12. At some point in time you decide you can't correct it. And so that is a programmable value. When we get to that value, that's when we say, oh, it's uncorrectable. From there, we get just simply an uncorrectable status. BCH told us how many errors, and it told us whether it corrected any or not, and that sort of thing. In terms of configurability, we, like most everyone else, have a compiler for both BCH and LDPC. This compiler allows us to create code that is structurally very different based upon needs. After the compiler is done with the process, then we get something that's parameterizable RTL. And then, of course, there's programmable abilities beyond that. And so, in a lot of ways, both of these are very similar in capability. That includes the amount of parity for either one. There's a number of types of flash, and they all exhibit different properties, but the thing I want to expose in this slide is the fact that we have a manufacturer that says we need 60 bits of correction, and that 60 bits is the worst case page, right? It is the absolute worst case page. So if you had the ability to correct different amounts in your ECC correction hardware, then you can save or you can add more storage space. You know, some of these are going to be pages that need half or quarter the amount of correction that the worst case page will have. And that would give you the ability here to, if you had a different correction amount associated with those pages, then you could actually save storage space and use more data rather than more parity on those particular pages. Here's kind of the takeaway. If you get nothing else, this is what I want you to take away here. Implementation choices. For enterprise, you really need to have a consistent latency. BCH is, of course, extremely stable latency, so it's an ideal case. But I'm sure if you talk to very many people, you're going to find out that BCH at 60 bits is just unreal in power and gates, right? You just can't implement something that big. And, you know, if we go to 120 bits in the future, BCH would more than double in size with 60 bits. And it's going to be a tremendous power-hungry thing on your ASIC. And so you want to minimize that. And LDPC does a good job. At about 50 bits and above, LDPC is lower in gate count and power. And as the number of bits increases, it's just going to get better in terms of the trade-off between BCH and the other. But LDPC has two different modes. It has hard decision and soft decision decoding. The hard decision decoding is extremely similar to BCH. Other than the iteration count, it has a latency profile that is very tight. And so I'm suggesting that if you have a requirement for latency like an enterprise, then you could go ahead and use LDPC, but just use hard decision decoding and pay a lot more attention to error rate as it comes off the flash devices. If you are more flexible, then of course it's just simply a trade-off, right? BCH or LDPC based upon powered gates. And then if LDPC wins that, then you can use both hard and soft decision decoding because of course the latency doesn't change a lot. In our world in Mobiveil, we have a LDPC IP, and it has these characteristics in TSM40G. You start here on the left of the graph and go from 0 PE cycles to end-of-life PE cycles. And this is the power profile you would get in correction. And the number of iterations, it goes from iterations of 1 to iterations of 3.5. So this is kind of the way in which we approach it. It's better in that we've characterized this for a whole bunch of different flash memories in 4 different types of memories. And we can prove the fact, at least to ourselves, that this profile can be done with just about any flash that's out there. Of course, our compiler and so on can give you a whole bunch of different choices. Weighting for LDPC, the higher the weighting, the faster it corrects. And so you have a lot of control over how you can create a LDPC module. The compiler itself takes care of most of these things in the platform, you know, what kind of library you're going to go to, how fast, you know, what's the performance level. We take care of the major scalability parameters for code word size and the like. And of course, there's a fair amount of parallelism that goes on, and that we can, based upon power and your needs of performance and parallelism, we can change that. The last part of this is we can have different amounts of parity, and it switches on the fly. We can have different correction codes. There's all kinds of different things we can do right on the fly. So it's a highly programmable device, even though it's, I think, a lot lower power and area than most anything out there on the market. For FPGA implementation, we have a lot of other additional options to optimize FPGA usage. Here we talk about, in order to use LDPC, you really have to have a characterization mechanism for flash. Like I was discussing earlier, you want to know what the error rate for certain pages are so you could program it. You need to know how to set thresholds for doing soft decision decoding. There's all these parameters that you need to be able to set. And we have an environment here where we can hook up a flash device to a board and then characterize that flash device in minutes. We have all the software and support necessary to do that in minutes. And so it can characterize that and give us a configuration file that will give us the ability to program our LDPC to work with that flash. You've probably heard about G and H matrices in LDPC, and those are held actually in SRAM. And so the SRAM can be reprogrammed to use any kind of different matrix that we would like to use. And yes, that is the end of the talk, and I could take questions if you have any.